Our planet, Earth, is a cradle, a starting point in the vast universe. But what if our future lies beyond the familiar blue skies and towering mountains? What if we could build homes amidst the stars, in structures so vast they dwarf our current comprehension? This is the captivating concept of space megastructures. These hypothetical behemoths, often found in science fiction, represent the pinnacle of engineering and imagination. But could they one day transition from the realm of fiction to reality? The idea of living inside a space megastructure sparks a sense of wonder and endless possibility. Imagine gazing out your window, not at a cityscape or a natural landscape, but at a breathtaking panorama of stars, a view unobstructed by atmosphere or the limitations of gravity. Imagine a world where resources are plentiful, where energy flows freely from the very stars that illuminate our night sky. The prospect is both daunting and exhilarating, challenging our understanding of what it means to live, to build, and to exist as a species. The allure of space megastructures extends beyond their sheer scale. It lies in the promise of a future where humanity transcends the confines of Earth. Imagine a society no longer bound by the limitations of a single planet. Picture cities sprawling across rotating habitats, bathed in the glow of an artificial sun. These are glimpses into a future that could one day be within our grasp. But the path to such a future is paved with monumental challenges. The engineering feats required would be unparalleled in human history. We would need to harness the power of entire stars and overcome technological hurdles. Yet, the human spirit is no stranger to overcoming odds. Throughout history, we have proven our ability to innovate and achieve the extraordinary. The journey towards space megastructures may be long, but the potential rewards make it worth undertaking. The term megastructure might evoke images of towering skyscrapers or sprawling cities, but in space it takes on a whole new dimension. Space megastructures are vast constructs, dwarfing our most ambitious projects. These colossal structures are self-contained habitats, supporting entire populations and ecosystems. Imagine cities within gigantic spheres, cylinders or rings, orbiting stars. Grounded in physics and engineering, they represent a pathway for humanity to expand beyond Earth. These structures could replicate Earth-like conditions, providing space for billions. Building them requires technologies far beyond our current capabilities. Yet, the potential rewards are immense. They offer solutions to Earth's resource limitations and safeguard against existential threats. From Dyson Spheres capturing star energy to O'Neill cylinders and Stanford Torus, these structures embody humanity's ambition to reshape the cosmos. Perhaps the most audacious concept in space megastructures is the Dyson Sphere, proposed by physicist Freeman Dyson in 1960. Imagine a colossal shell enveloping a star, capturing its energy. This energy could power an advanced civilization. The scale is difficult to comprehend. It would be at least the size of Earth's orbit. Constructing it would be an unparalleled engineering feat. Yet, the potential rewards are staggering. Capturing a star's energy could sustain a civilization for millennia. The Dyson Sphere continues to captivate scientists and science fiction enthusiasts. It reminds us of the boundless possibilities in space exploration. While the Dyson Sphere represents a grand vision of harnessing the power of stars, the O'Neill cylinder, conceived by physicist Gerard K. O'Neill in the 1970s, offers a more tangible approach to creating habitable space megastructures. Imagine a colossal rotating cylinder, housing a self-contained ecosystem and providing artificial gravity. These rotating habitats would generate gravity through centrifugal force, mimicking Earth's gravity. Within these massive cylinders, entire landscapes could be crafted. Lush forests, rivers, and bustling cities could rise amidst rolling hills. The interior surface would be a canvas for diverse biomes and ecosystems. Imagine strolling through a Mediterranean-style vineyard under a simulated sun, then venturing into a tropical rainforest teeming with exotic life. Life in an O'Neill cylinder would be a blend of technological marvel and natural wonder. Inhabitants would live in a controlled environment with regulated weather patterns and day-night cycles. The construction of O'Neill cylinders is considered more achievable than Dyson spheres, utilizing resources from the Moon, asteroids, or Mars. The O'Neill cylinder offers a compelling vision for humanity as a spacefaring civilization. The Stanford Torus, developed at Stanford University in 1975, presents an intriguing variation on rotating space habitats. Imagine a massive donut-shaped structure, several miles in diameter, spinning in space. This spinning motion generates artificial gravity, providing a comfortable living environment. Unlike the enclosed O'Neill cylinder, The Stanford Torus features an open roof, allowing for breathtaking views and natural sunlight. Mirrors could reflect sunlight inside, reducing energy demands and creating a comforting environment. The Stanford Torus represents a more achievable step towards space colonization compared to a Dyson Sphere. Utilizing in-situ resources like mining asteroids makes the concept feasible. Exploring these concepts is crucial for preparing humanity to venture beyond Earth and establish a lasting presence among the stars. The dream of living within space megastructures hinges on overcoming a formidable obstacle: the development of technologies capable of constructing these behemoths in the harsh and unforgiving environment of space. Bringing such ambitious projects to fruition would require advancements in multiple fields, pushing the boundaries of material science, robotics, and energy generation. Imagine automated factories in orbit, churning out components from asteroid-derived metals, or swarms of autonomous robots assembling massive structures with precision and speed. One of the key challenges lies in developing materials that can withstand the extreme temperatures, radiation, and micrometeoroid impacts of space. Current spacecraft materials, while robust, are not designed for the immense scale and structural demands of megastructures. Scientists are exploring new materials like carbon nanotubes and self-healing alloys, boasting exceptional strength and durability, capable of withstanding the rigors of space for extended periods. Equally crucial is the advancement of robotics and automation. Constructing megastructures would be a task of unimaginable complexity, requiring millions, if not billions, of coordinated operations. Autonomous robots, capable of working tirelessly in the vacuum of space, would be essential for assembling components, welding seams, and performing intricate maneuvers. Imagine swarms of specialized robots, each programmed for specific tasks, working in unison to create structures of awe-inspiring scale. Beyond materials and robotics, energy generation presents another significant hurdle. Powering a space megastructure would demand an abundant and reliable energy source. While solar energy is a viable option, especially for structures closer to the sun, other possibilities like fusion power or even harnessing the energy of black holes are being explored. The ability to generate, store, and distribute vast amounts of energy would be crucial for maintaining a habitable environment and powering the myriad systems within these colossal habitats. Constructing megastructures on Earth is a feat in itself, but assembling them in space presents a whole new set of challenges. The absence of gravity, while offering advantages for moving massive objects, also introduces complexities in terms of stability, positioning, and maneuvering. Traditional construction methods would need to be reimagined, paving the way for innovative approaches tailored to the unique demands of space. One promising concept is modular construction, where individual components are fabricated on Earth or in space and then transported and assembled in orbit. These modules, containing everything from living quarters to life support systems, could be standardized for easy replication and interchangeability, streamlining the construction process and allowing for flexibility in design. Imagine a megastructure gradually taking shape as modules dock and lock into place, expanding the habitat one piece at a time. Another approach involves utilizing in-situ resources, such as mining asteroids or the moon for raw materials. This would significantly reduce the need to transport materials from Earth, minimizing costs and reliance on terrestrial resources. Imagine mining robots extracting metals and minerals from asteroids, feeding a steady supply of materials to orbiting factories where they are transformed into components for the megastructure. 3D printing also holds immense potential for space construction. Large-scale 3D printers, using lunar or asteroid regolith as feedstock, could fabricate entire sections of a megastructure in space, eliminating the need for extensive assembly. Imagine a 3D printer the size of a small moon, extruding layer upon layer of material, gradually building walls, floors, and even entire landscapes. Mastering space-based construction would be a game-changer, opening up possibilities not just for megastructures, but for a wide range of space-based infrastructure, including space stations, research outposts, and even interplanetary spacecraft. Accessing the solar system's resources is crucial for living beyond Earth. Solar and fusion power are key to sustaining space habitats. Imagine a Dyson ring capturing a star's energy. Transitioning to space habitats requires significant adaptations. Space megastructures will shape new social and cultural dynamics. Life in space megastructures will blend work, education, and leisure. Psychological well-being and social cohesion are crucial in space. Space megastructures face significant risks and challenges. Ethical considerations are vital in space exploration. Space megastructures have far-reaching economic and social impacts. Space megastructures are an investment in humanity's survival. Space megastructures offer boundless possibilities for humanity. The pursuit of space megastructures is not merely about escaping the challenges of Earth. It's about embracing a future filled with opportunity, growth, and wonder. It's about pushing the boundaries of what's possible, challenging ourselves to achieve the extraordinary, and ensuring the long-term survival and prosperity of our species. As we stand at the cusp of this new era of exploration, we are reminded of the words of Carl Sagan, who said, "The Earth is a very small stage in a vast cosmic arena." Space megastructures represent our ambition to move beyond that small stage, to become a multi-planetary species, and to write the next chapter in the human story. The challenges ahead are formidable, but so too is the human spirit. We are a species of explorers, inventors, and dreamers, with an unquenchable thirst for knowledge and an unwavering determination to overcome obstacles. The journey towards inhabiting space megastructures may be long and arduous, but it is a journey well worth taking, for it holds the key to a future filled with boundless potential. The future awaits us among the stars.